So, yeah, welcome to the NPTEL problem solving session of the course Robotics, Basics and Selected Advanced Concepts. Okay, so the focus of this week was, a discussion on redundancy and redundancy resolution. Okay, so and we'll be going through most of the lecture notes only. Okay, so to discuss, to get a gist of what is redundancy, what is redundancy resolution, what are the different approaches for redundancy resolution, we'll be discussing. So the first part is what is redundancy actually. Okay, so you know that there are two terms, right? One is the degree of freedom of the robot and other is the number of actuators present. So whenever the degree of freedom is more than the number of actuators, okay, so basically it's a over constrained case. Okay, so there is no solution in this particular case. Okay, but whenever the degree of freedom is equal to the number of actuators, okay, this is called a fully constrained. Okay, and this particular case has a unique solution. Okay, and whenever the third case happens, whenever the degree of freedom is less than the number of actuators, so basically there are more ways to manipulate degree of freedom of your robot. There is not just one way. There are multiple ways. In theory, infinite ways. That is what we call the redundant. Redundant case. So that is when the robot is redundant, when the number of actuators is more than the degree of freedom of the robot. Okay, so like we took the first example of the 2R manipulator. Okay, so 2R manipulator. Okay, so this particular 2R manipulator has two DUF and it also has two actuators, one at the ground and one at the you know joint between link 1 and link 2. Okay, so what it essentially means is, as we saw, that there will be a unique solution, but unique solution for which problem? Okay, so basically there will be a unique solution for both the problems. Which both problems? Your forward kinematics and inverse kinematics. Okay, so and now discussing further, you will see that the forward kinematics problem in general always has a solution. Okay, you know, in the domain of theta 1 and theta 2, if it is possible for you to set a particular theta 1 and theta 2, you will get a corresponding x and y, right? There is no uh, doubt in that. Okay, so for any theta 1, theta 2, or for any vector theta, you will get a particular x. Okay, but what happens is, okay, when you try to get theta for a particular x, okay, for given the position of the end effector, what are the joint angles? Okay, and if even for 2R case, if this x, okay, or these coordinates are in the workspace of the robot, okay, if x is in the workspace of the robot, okay, workspace of the end effector, then a unique solution exists for this problem also, that we had already derived in previous lectures. Okay, so this is a fully constrained robot for which a unique solution exists. Okay, but when you talk about a 3R robot, okay, so a 3R robot has 2 degree of freedoms, right? 3R robot has 2 degree of freedoms because again the end effector moves in a plane. It's a planar 3R robot, so end effector moves in a plane. In our case, we can say that it moves in the XY plane. Okay, but it still has three actuators, three independent actuators. Okay, so now from what we had discussed earlier, this is what we call a redundant robot. Okay, and what it actually leads to is, you can see that, as we discussed earlier, that forward kinematics, given the joint angles, x and y will always exist. Okay, so given theta 1, theta 2, and theta 3, right? Given we can calculate x and y always in the domain of theta 1, theta 2, and theta 3, right? If you can give some joint angle, that will lead to some end effector position, right? It may or may not be unique, like it, like x and y will be unique, but you can get the same x and y for multiple pairs of theta 1, theta 2, and theta 3, right? Because we saw that there are two theta 1 and theta 2, two set of theta 1 and theta 2 that lead to a particular x and y, that lead to the same x and y. Okay, we call them the branches of the inverse kinematic solution. Okay. But you see, there will be some x and y that will exist, right? So in this case also, forward kinematics exists always. Okay, so there is a unique x that you will get. Okay, like we should not say unique, but you will not get infinite x, right? But when you start talking about the inverse kinematics of the 3R robot, okay, this is where the you know redundancy or the concept of redundancy starts becoming more clearer. Okay, why? Because you see, what is inverse kinematics basically? Okay, so what you have is your direct kinematics or forward kinematics, right? For any robot. Okay, and using the forward kinematics, you say that for a given x and y, you want to find, your theta 1, theta 2, and theta 3, basically your joint angles or the inputs to the robot you want to find. Okay, so if we, you know, see this problem, from a direction of solution of nonlinear equations, okay, there are two equations, okay, and we want to solve for three variables, okay, and that is the classic case when there are infinite solutions, right? When there are more variables than the number of equations that are available, right? So, okay, so just continuing on the discussion that we had earlier, okay, when there are the degree of freedom but less than, but greater than the number of actuators, okay, so there was one input variable, okay, okay, one actuator if we say, and we had two equations, right? Because the degree of freedom is two, so there are two degree of freedom for an end effector. So in that particular case had no solution. Like this checks out from the theory also that we know. And when the number of variables is equal to the number of equations that we have, that is when you get a unique solution, right? And we had already seen that in case of the 2R manipulator, right? So this is what redundancy means, that you have more variables that can be controlled, but you have less number of equations to specify exactly how those variables have to be controlled. Okay, I mean, one more way to get a feel for the redundancy of this problem, okay, to get a feel for the infinite solution is basically, since you have two equations but three variables, right? You have theta 1, theta 2, and theta 3 for the 3R manipulator. Okay, using the two equations you can calculate theta 1 and theta 2, right? But then you can choose any value of theta 3 and it will still give you a solution. So basically there are infinite possibilities for theta 3. This is what leads to the infinite solutions, okay, like in one sense. This is how you can think of the solution to the inverse kinematics of 3R manipulator having infinite solutions. Okay, so what do we do in this case actually? Okay, so what we want is, you know we want a unique solution. right? So, you know, what we, going by the theory of nonlinear equations, if whenever there are, more variables than the number of equations, what we used to do was we used to introduce constraints, right? Because the constraints, you know, they give us additional equations. Okay, so this is, where the concept of redundancy resolution comes in. When, you want to pick a particular solution out of the infinite possible solutions. Okay, you want to get a unique solution. Okay, out of those infinite values. Okay, so if you want to get a unique solution, you need to specify, okay, the missing, you know, the missing way in which you want to get your solution. Okay, and you know, we saw that there are three variables, you had two equations, and when you introduce one more constraint, that basically leads to one more equation. So finally, you will end up with equal number of variables and equal number of equations, and that will give you a unique solution. Okay, so basically this constraint is this extra way of specifying how you want your, you know, variables to be, right? And in the particular case of the manipulator, okay, if you fix theta 3, right? If you say theta 3 is a constant, right? So this is a constraint, and this acts as the third equation, right? And once you have fixed theta 3, then this is no longer a variable, right? So then only theta 1 and theta 2 are variables. So basically then you have two variables and two equations. So there will be a new unique solution, right? So this is how introduction of constraints, you know, uh, we use additional constraints to resolve redundancy in manipulators. Okay. Another approach, is optimization based approach. Okay. So what is essentially done is, for the solution of, you know nonlinear equations, okay, whenever there are infinite solutions and you want to get a unique solution, okay, or you can think of it like that since there are infinite solutions, it means there are possibilities of, specifying extra, you know uh, there is a possibility that you can specify a particular kind of motion that you want. Okay, for example, you may want a very energy efficient motion. Okay, since there are multiple motions that are possible, in theory, infinite motions that are possible, each one of them will have a different energy consumption, right? So, what is wanted is a particular motion that minimizes the energy. That is that is one way of giving extra information, or giving the extra constraint or the extra equation that is needed to get the solution. Okay, in your lecture notes or the lectures, one particular way that was discussed was, you know, uh, defining a cost function that minimizes the joint angles. Okay, that minimizes the absolute joint angles. Okay, so now in this particular case, the inverse kinematics problem is posed as an optimization problem with this given constraint. Okay, so this is the, for formal way in which how the optimization problem is defined, that minimize this cost function, that is theta 1 square theta 2 square plus theta 3 square, you know over, this theta variable, over the variable theta, subject to the constraints of your forward kinematics. Okay, because irrespective of any solution that you get, it should always satisfy the forward kinematics. Okay, and there are two constraints, right? Because there are two forward kinematics equation. One is for the x direction, one is for the y direction, and you can club them, in a vector, okay, to just make the representation much more clearer. Okay, so if it is written in terms of the the substitutions that we have made, okay, so this is, let us call this fancy C, right? So minimize the cost function over the variables subject to the constraints, right? Okay, and this is the standard form of writing the constraint, that g of x or the theta, whatever your variable is, equal to 0. That is why the forward kinematics constraint have been written like this. Okay, and then to solve this optimization problem, okay, you can use some existing solvers also. For example, the fbincon function that is available in MATLAB. Okay, or what is also done is you can try to solve it by hand. Okay, by using the analytical method that exists. So one is the Lagrange's method. Okay, to solve optimization problems. Okay, so you know this is the method that introduces the Lagrange multipliers. Okay, so what you do is you define a quantity L, okay, that is equal to the cost function plus, you know, your some constants. Okay, so there is one scalar constant for each constraint equation. Okay, there are two constraint equations, therefore there are two scalar constant, lambda 1, lambda 2. We stack them in a vector and call that vector as lambda under 1. Okay, so this is essentially your C plus lambda 1 G1 plus lambda 2 G2. Okay, G1 and G2, we are calling the first equation as G1 and the second equation as G2. Okay, and once after once you have defined this particular quantity, you have introduced two more variables, lambda 1 and lambda 2, right? But after introducing this particular quantity, this constrained optimization problem, okay, becomes an unconstrained optimization problem, you know, over the new cost function. Okay, so if you know write your both, we'll discuss this. Okay, so minimizing just C over theta subject to g of theta equal to 0. This is equivalent to minimizing the Lagrangian over theta and lambda, right? So there are no constraints in this case, and wherever there are no constraints, and you have a and whenever there are no constraints and you have a scalar function and you want to minimize it, what is done is, okay, you take the partial derivative with respect to the variables, right, equal to 0, and the next is lambda equal to 0. Okay, so what this leads to actually, the first, you know, this partial derivative will give you three equations, and the second one, it will lead to two equations. Okay, so finally you end up with five equations, and there are in total five variables, right? Theta 1, theta 2, and theta 3, and the additional your lambda multipliers, lambda 1 and lambda 2, Lagrange multipliers, lambda 1 and lambda 2. Okay, so since there are five equations and five variables, this will lead to a unique solution, and that is what was required for redundancy resolution. Okay, so this particular problem, it dealt with only minimizing the squared, absolute angles. Okay, but in the notes, there is a lot of discussion. So this is the particular problem that we have discussed right now, and the other way of resolving redundancy is using the pseudo inverse based approach. Okay, so using the pseudo inverse of the Jacobian mapping of the velocity relations, and it is written on this slide that it minimizes your squared velocity. Okay, so what that means is that in that particular case, okay, it is still minimizing for theta, but the cost function now, instead of just the angles, instead of just minimizing the angles, we are minimizing the velocity. Okay, subject to the same constraints, because irrespective of what angles you get, they should always satisfy your forward kinematics. Okay, and then there was a, yeah, so this is how you can write that particular approach in optimization form. And then there was a discussion on using backbone functions. So you can think of it as using basis functions to approximate theta, right? So using optimization, you approximate the contribution of the particular basis function based on any cost function that you have. Okay, so you can get more information about this in this paper. I would highly encourage you to read this paper. And then another approach that Sir had discussed in quite detail in previous week lectures also, and in this week also, is the tractrix based approach. Okay, so in the tractrix based approach, every link has a velocity along the length of the link always. Okay, so as Sir had discussed in the lectures, this leads to some very nice properties for redundant robots, in a sense that the head moves the most, right? And the base moves the least. So that actually helps you in planning or navigating around the obstacles. So this you might remember from your lectures. So like if you have not seen the lectures, you should see them. And then there is an algorithm to calculate the inverse kinematic solutions based on the tractrix approach for a redundant robot. And then there were some results from a publication that Sir had used and the experimental setup. Okay. Uh, so, mm, yeah. Now discussing the applications of tractrix-based approach. So, before just discussing that, I mean, Sir have already discussed the applications, but one thing that I would like to point out about this particular approach is that the Tractics algorithm, it is of linear complexity. Okay, and whenever we are designing robotics algorithms, the computation we try to keep the computational complexity as low as possible, right? And one thumb rule is that linear complexity, linear computational complexity is good. Okay, so the computational time scales linearly with the number of variables that you have to solve for. Why this is important is because most of the time you will not be using your powerful desktop grade processors in your robots. Okay, so on robots there will be small processors that consume less power, and therefore they are designed to not run as fast as your desktop grade processors because they have to consume low power. And on those intermediately fast processors, you need your algorithm to be as fast, as efficient as possible. Okay? So as to control the robot with a fast enough update rate. Okay, so this is one of the advantages of the tactics based approach. Okay, and again, this one of one more advantage is it appears more natural for particular robots. For example, the snake robot that Sarah also discussed. Okay, and then there was some discussion on collision detection. Okay, so there are many different methods of collision detection. This particular method is a very simplified method in which you're approximating all the links with spheres and then checking if the spheres are colliding or not. Because checking collision for spheres is quite easy. You just have to check if the distance between the centers is greater than or less than the link length of the robot. Okay, but this of course will not give you the actual collision status. But for the tractic, for that particular approach, the tractics based approach, this works well enough. So then there was obstacle avoidance using the same tractics based approach. And sir had already discussed this before also. And then there was a discussion on efficient representation. Okay, so why efficient representation? Since we, similar to the discussion that we had for efficient algorithms, you need to have efficient representations that you are going to use for your algorithms. Because again, the resources, the hardware resources that you're going to use on your robot will be very limited because again, they cannot use too much power and they cannot be too heavy. And since either you use the hardware that is sufficient for the model that you have developed, or you use the mod, or you develop a model keeping into account the resource constraints that are there on your robot. Okay, so your representations should be as light and efficient as possible. Okay, so that the algorithm can run fast enough. Okay, like not very fast, but the algorithm should be able to run fast enough for the robot to be able to react in time. Okay, and then there was a discussion on endoscopes. So yeah, so I think this endoscope was also discussed in the flexible manipulators lecture, the lecture 3. Okay, so and then there was a discussion on redundancy resolution for a human arm. Okay, and then there was one more application of redundancy resolution. It was that of the redundancy resolution for like reshaping the velocity ellipsoid. Okay, so what is the velocity ellipsoid? So velocity ellipsoid is essentially gives you the information on how easier it is for your end effector. Um, Hello, Mukesh. Am I audible? Yeah, let's continue. Okay, so if the ellipsoid is longer in a particular direction, it means that to move in that particular direction with a given velocity, the joint velocities will be comparatively lower if the end effector were to move with the same velocity in the direction of the shorter side. So the shorter the or the narrower the ellipsoid gets, it to travel along the shorter direction of the manipulative ellipsoid, okay, or to travel along the minor axis of the ellipsoid, the joint rates will be much higher. Okay, and whenever the velocity this ellipsoid collapses, right, that the minor axis becomes zero, or any one of the axes, this becomes zero. That corresponds to a singular configuration. Okay, so in this particular uh, application of redundancy resolution, we are using this constraint on velocity ellipsoid, that it should always be a circle and not an ellipsoid. So basically, it should be equally easy for the robot to move in any of the two directions. This is what this whole section is about. Okay, and then there was a discussion on redundancy resolution in human arm, and how this force field adaptation task is carried out. So that arm had to go from the start position to the target position, and then there was a force field, and then it was just a study on how redundancy helps in l- uh, learning, or adapting to the force field. Okay, yeah. So I think most of these, uh, not most, almost all of the problems in the assignment for this week are directly from the lectures. So if you go through the lectures, you should be able to go, you should be able to do all the questions. And in this last section particularly, this robot, yeah, the flexible cable-driven robot. So this is a pretty simple robot, and if any one of you has access to 3D printer, you can try to make it and you can try to control it. It will be fun, right? And also, this suggested additional reading that is given at the end of these lecture notes, I would really encourage you to go through at least some of them. It will give you a broader perspective on on all these concepts related to redundancy and redundancy resolution. So I think we will finish. Yeah, we will wrap up the session for today, and you can find this video. If you have any doubts, you can ask on the forums for the course. Okay, thank you.